Comparing two variances. Our main objective in these lectures is to perform a two-sample F test to compare two variances. Also, how to interpret the F distribution and use an F table to find critical values. So here we say let S1 square and S2 square represent the sample variances of two different populations. Now we have two conditions here. If both populations are normal and also the population variances are equal, that is the two population variances are equal, then the sample distribution of is F equal to S1 squared divided by S2 squared. And we call this the F distributions. Now we have a properties for the F distribution. One, the F distribution is a family of curves, each of which is determined by two types of degree of freedoms. So we have the degree of freedom corresponding to the variance in the numerator, which is DFN, and also for the denominator, the degree of freedom corresponding to the variance in the denominator. Now, the F distribution are positively skewed. And also the total area under each curve of an F distribution is always equal to 1. Also, the F values are always greater than or equal to 0. And also for all F distribution, the mean values of F is approximately equal to 1 also. So critical values for the F distribution, first thing we need to do is to specify the level of significance, which is the alpha. And also we need to determine the degree of freedom for both the numerator and also the denominator, which is DFN and also DFD. Then we can use the table 7. Again, the number of the table depends on the textbook you are using. Again, this is the F table, the F distribution table. So we use table 7 in appendix B to find the critical value. If the hypothesis testing is either one tail, we use the F table. If it's two tail, we use the half alpha F table. So if it's one tail, we use the alpha F table. If it's two tail, we use half alpha table. Again, we're going to see an example. So here they say we should find the critical value for a right tail test when alpha is 0.05, degree of freedom for the numerator is 6, degree of freedom for the denominator is 29. So here we almost have all the values and we go straight to the table. So this is how the table looks like. And here we can see, first of all, we have our degree of freedom for numerator, then degree of freedom for the denominator. So the columns are degree of freedom for the numerator, and the rows are the degree of freedom for the denominator. So the denominator is 29. So we have to go to row 29. Then the degree of freedom for the numerator is 6, and we went to 6. So the FO we give, the critical value will give us 2.43. And also here we are, the alpha is 0.05, and it's only one tail, right tail. So we are using alpha, not half alpha. Now the next, they say, okay, so here we have found the critical value F value for two tail. So now we have to use half alpha, two tail. Again, here the alpha value is given, degree of freedom is given for numerator and also for the denominator. So when performing a two-tail hypothesis testing using F distribution, you need only to find the right tail critical value. So you must remember to use what? The alpha half table. So half alpha equal to half 0.05. So that will give us 0.025. Again, if we divide 0.05 by 2, we get 0.025. Now, why are we doing this? Again, because we are performing a two-tail hypothesis testing. So next, we know the half alpha is 0.025. We also know the degree of freedom for both numerator and denominator. So here we can see our table. We are using alpha is 0.025. Now we know the degree of freedom for the numerator is column, denominator is row. So we go to 4 and 8, and that gave us 5.05. So the critical value is therefore equal to 5.05. Now, to use sample F test for variances. So again, the first two examples, we learned how to find only the critical value. Now we are going to perform hypothesis testing now. So here we say to use the two sample F tests for comparing two population variances, the following must be true. First, the sample must be randomly selected, and also the sample must be independent. So each population must have a normal distribution. Now, to find the test statistics, F is equal to S1 square divided by S2 square. And as we said earlier, S1 square and S2 square represent the sample variances, with S1 square greater than or equal to S2 square. Now, the degree of freedom for the numerator is DFN, which we use the formula N1 minus 1. Now, N1 is the size of the sample having the variance S1 square. Then the degree of freedom for the denominator is DFD equal to N2 minus 1. Also, the N2 is the size of the sample having the variance S2 square. So now let's follow the steps for hypothesis testing. As usual, we start with stating the HO and HA. Again, HO is always our claim, so we identify the claim, then we state the null and alternative hypothesis. Then we have to identify the alpha or specify the level of significance. Then we identify the degree of freedom. In this case, we have the degree of freedom for numerator and also the denominator, which will be N1 minus 1 and 2 minus 1. Then we determine the critical value using the table 7 in Appendix B, that's the F table. Now we can determine the rejection region if we know the critical value. Then the next step is to calculate the test statistics, which is S1 squared divided by S2 squared. Next, we know the test statistics and also we know the critical value, so we can make a decision either to reject or fail to reject the null hypothesis. And here we say that if F is in the rejection region, then we reject HO. Otherwise, we fail to reject HO. Now we need to interpret the decision in the context of the original claim. So let's see an example. And here we are performing again two sample F tests, which again is hypothesis testing. So here, restaurant manager is designing a system that is intended to increase the variance of the time customers wait before their meals are served. Under the old system, a random sample of 10 customers had a variance of 400. Under the new system, a random sample of 21 customers had a variance of 256. At alpha equal to 0.10, is there enough evidence to convince the manager to switch to the new system, assuming both populations are normally distributed? So this is one major condition. Performing two sample F tests, the populations might be normally distributed. So we almost have all the values here. We have the sample sizes for the two and also their variances. So let's start with the hypothesis testing. The first thing, we state our HO and HA. Then the next step, the alpha value is given to us. Degree of freedom based on a sample size. We can find the degree of freedom here is 9 and also 20. Now, if we look at our question, we can see the customer is first is 10, so 10 minus 1. The second one is 21, 21 minus 1. So that's why the degree of freedom is 9 and 20. So if we know the degree of freedom for the numerator and the denominator, then we can be able to find the critical value. and come up with our rejection region. So here our critical value given here. Again, our alpha, this is a one tail. So we are using 0.10, the alpha value, and we have 1.96 from the table. Now we can find the test statistics, which is S1 squared divided by S2 squared. So 400 divided by 256, and that gives us 1.56. Then we can, here we say we fail to reject HO. Why? Because we can see 1.56 is less than 1.96. So it fell under the rejection region. Same concept as the chi-square we covered earlier. If the test statistics value is greater than the critical value, then we are going to reject HO. Here in this case, the test statistics value is less than the critical value. So we fail to reject HO. So here we can say our interpretation means there's not enough evidence to convince the manager to switch to the new system. Now let's look at the second example. Here we say we should perform a two-sample F-test again. You want to purchase a stock in a company and are deciding between two different stocks. Because a stock's risk can be associated with the standard deviation of its daily closing prices, you randomly select samples of the daily closing prices for each stock to obtain the result. So at alpha equal to 0.05, can you conclude that one of the two stocks is riskier investment, assuming the stock closing prices are normally distributed? So here we have stock A, our N2 is 30, S2 is 3.5. Stock B, N1 is 31, S1 is 5.7. So we have enough data to, and also we know the alpha value is 0.05. So we can do our hypothesis testing. So the first thing we are going to state our HO and HA. First of all, because we know 5.7 square is greater than 3.2 square. And S1 square will give, again, S1 was given to be 5.7. So S1 square, here we are doing variance, not standard deviation. So that means 5.7 will be square, 3.5 also will be square. The value of a standard deviation square will give us the variance. So here we are doing two-tail because the question said equal and not. So HO said they are equal, HA said not equal. Because it's two-tail, we use half alpha. So that will give us 0.025. The degree of freedom will be what? Numerator, the sample size was 31 and 30. Let's look at the table. So into 30 and 31. So we get 30 and 29. So with this degree of freedom for numerator and denominator, we can find the critical value. The critical value was 2.09 from the table. So next we need to find the test statistics, and from there we can know whether to reject or accept HO. So 5.7 squared divided by 3.5 squared. That gave us approximately 2.67. Okay, so 2.67 is greater than 2.09. So this time we are going to reject HO. So our interpretation means, remember, equal. We reject equal means not equal. So there's not enough evidence to support the claim that one of the two stocks is a riskier investment. So we reject again HO. So that will be the conclusion of this lecture. Again, this lecture will first of all learn to interpret the F distribution, what is the concept of F distribution, and also how to find a critical value using the F table. Then we saw two examples on how to perform hypothesis testing for two sample F tests to compare the two variances. Again, see you in the next lectures, and thank you for your time.